Metamorphic rocks, as their name implies, have been physically and/or chemically altered. This has happened by heat alone or heat and pressure over extended periods of time. The most common settings where metamorphism occurs are at a contact or local setting, where the changes to the rock are caused predominantly by heat, and in a regional scale setting, where the changes to the rock are caused by both heat and pressure. There are other, less common types of metamorphism, but we'll focus on local and regional metamorphism here. It's good to know that the parent rock type of metamorphic rocks can be igneous, sedimentary, and even other metamorphic rocks, and that this affects the degree of change that occurs. For example, if your parent material is a shale, a sedimentary rock type, you can have a range of daughter rock types depending on the grade of metamorphism. This is important for engineers to know as it dictates the mineral assemblage remaining. Contact metamorphism can occur where magma intrudes into the crust. The adjacent pre-existing rocks are metamorphosed due to the high temperatures of the magma. Sometimes gases and infrequently pressure can also play a part in the metamorphism. The zone of altered rock around the intrusion is called the metamorphic aureole. This zone will be greater for larger plutonic intrusions compared with smaller scale dikes and sills. The exact thickness of the aureole will depend on many other factors, including the mineralogy of the original rock and the temperature of the intrusion. The thickness can be up to the kilometre scale, but is more typically of the order of meters or less. As the host rock has been altered, it is given a new name depending on the grade or amount of metamorphism and the mineralogy of the rock. Typically, contact metamorphic rock examples are marble from limestone, hornfels from shale or claystone, and quartzite from quartz sandstone. In addition to recrystallization and mineral changes, the temperature and the pressure from the intrusion forcing its way up weakness planes in the rock can lead to the formation of closely spaced joints adjacent to the intrusion. Regional metamorphism occurs over vast areas, up to hundreds of square kilometres, due to very high temperatures and pressures. This is typically associated with the large-scale forces of plate tectonics. In regional metamorphism, rocks that form closer to the margin of the tectonic plates, where the heat and pressure are greatest, often differ in their minerals and texture from those that form farther away. During metamorphism, the rock generally remains in the solid state. The process of metamorphism generally starts at about 200 to 300 degrees Celsius. The stages of metamorphism include compaction, where the grains move closer together, reducing the porosity and creating a denser rock. Recrystallization, where the crystals change size and/or shape without changes in mineralogy. The creation of new minerals due to the rearrangement of atoms in the original crystals. And finally, the formation of new crystals through chemical reactions altering the original minerals. The stage reached will depend on the temperature and pressure imposed on the original rock. Changes in the fabric of the rock are typical in regional metamorphic rocks. At plate boundaries, there is typically a large inclined maximum principal stress acting in the direction of plate movement. This will force the newly forming crystals to elongate perpendicular to the maximum stress direction. This produces a rock that is schistose, with a low shear strength parallel to the schistosity. This can have significant consequences for the design of slopes and dams. Regionally metamorphosed rock environments can often be expected to have this evidence of schistosity. As the environments were formed under high pressure, you may also expect faulting in brittle rocks and folding in ductile rocks. Igneous intrusions like dikes are also common as they are associated with the high temperatures that form the metamorphic rocks.